As the Pulitzer Prize-winning author Douglas Hofstadter explains, it turns out that an eerie type of chaos can lurk just behind a facade of order. And yet, deep inside the chaos lurks an even eerier type of order. Let's talk about that coin flip we discussed earlier. Not even the smartest person in the world can predict the result of this coin flip. Think of all the factors that are involved in deciding the result. Air currents, minuscule changes in gravitational forces, air resistance, not to mention the vast variability in the process of sending a neural message from my brain all the way down my body through nerves so that muscles in my hand can either contract or expand a certain amount. Naturally, no one could possibly predict the result of the coin flip. But as every first grader knows, approximately 50% of the flips will result in heads, and 50% will result in tails. In chaos theory, this probability is known as an attractor, because over time, the complicated events are attracted to this single simple point. But not all attractors are as simple as coin flipping. In our example, the results are drawn to a single fixed point. So this is called a fixed point attractor. Fixed point attractors are the simplest type of attractors. There's a special type of attractor that fascinates scientists called strange attractors. Strange attractors. Strange attractors. Stop it! Strange attractors are attractors that, instead of being drawn to a point, a curve, or some geometric shape, are instead drawn to a complex shape. A classic example of a strange attractor is the Lorentz attractor, created by Eddie Lorenz. The Lorentz attractor is a three-dimensional, parametrically defined system governed by three differential equations, each relating to one of the three dimensions. For those of you who don't speak math, imagine Billy from Family Circus, who leaves behind a dotted line everywhere he goes. Now imagine that Billy can fly, too, which means that he can move in all three directions, up, down, left, right, and forward, backward. So if Billy is governed by the equations of the Lorentz attractor, the direction and speed that he goes in will depend on where he is. And as he moves, the speed and direction that he moves in will change too, but he'll always leave that dotted line behind him. This system is a good example of the butterfly effect, because even a small change in Billy's initial position will send him in a different path. But that's only half the story. No matter where we start Billy off, the lines that show us where he's been will be attracted to the same unusual shape. So our Billy is drawn to the Lorentz attractor, just as the Billy in Family Circus is drawn to heartwarming shenanigans. Oh, Billy! Even though his path is not exactly the same when his starting point is changed, the basic shape remains the same. Therefore, the Lorentz attractor is a strange attractor. So through attractors and strange attractors, we can see chaotic movements being drawn to orderly events. So what have we accomplished from all this? Well, there are two main theories in the area of randomness, and we've just proven that they're both possible. In our universe, we perceive both order and chaos. So for a theory to be correct, it needs to explain the existence of both. This is Denny the determinist. He believes that on the quantum level, things operate through only cause and effect. In other words, randomness does not truly exist. Obviously, in this theory, order would exist. But what about chaos? Well, earlier we showed that we can perceive orderly events as chaotic because we aren't seeing the whole picture. So we would perceive chaos in this universe. Therefore, it could be a possible explanation. This is Ned the non-determinist. He believes that on the quantum level, things are truly random. In other words, the opposite of what Denny said. The existence of chaos in this universe is explained by chaos theory, where chaotic events on the subatomic level expand to become chaotic events on a viewable scale. And the existence of order is explained by the theory of attractors, where random events are drawn to orderly events. So this could easily be correct too. Now, I know this is a physics video, but I feel like we should view this problem from all sides. So, what's the philosophical take on all this? Our two groups, determinists and non-determinists, each have their ideas on what our existence is, and what's driving our universe. Oh, that sounds really tough. Let's just play some music. This is one of Denny's favorite songs. He likes it because it reminds him of what he thinks the universe is. This is one of Ned's favorite songs. He likes it because it reminds him of what he thinks the universe is. Now wasn't that fun, kids? I suppose a little explanation is in order. You see, Denny's song was what it was because every note had been placed in a certain place for a reason. Every arpeggio, triplet, and crescendo was written out beforehand because they all added something to that song. Even the tiniest note had a purpose, because without it, the song would not be the same. Now, Ned's song was what it was because there was that element of random in it. Before I started playing it, I only had a general idea of what I wanted the song to sound like. I didn't know the exact notes until I started playing them. I let my knowledge of tempo, key, and style guide me as I improvised every note. But as you might have noticed in Ned's song, even though I was improvising, the song still was attracted to that same basic tune. Chaos and order.